Every single day, there's this invisible army at work keeping you safe from threats you can't see, taste, or even smell. So today, we're going to pull back the curtain on their world. We're going to follow one single water sample on its journey through an environmental lab to uncover the incredible science that protects all of us. It all kicks off with a really simple question. You look at a glass of water, right? It looks totally clear, perfectly fine. But what's really in there? I mean, is it actually safe? That's a question that affects every single one of us. And believe me, the answer isn't always so obvious. So to get that answer, our water sample shows up right here at an environmental testing lab. This is where the world you can see meets the one you can't. And the journey from this simple-looking sample to a final definitive safety report, well, it's a pretty incredible dance between precision and high-tech gear. Okay, let's get into it. Before we can measure a single thing in our sample, we need a perfect, totally trustworthy ruler. I mean, you wouldn't try to measure a table with a stretchy rubber band, right? Of course not. And in chemistry, it's the exact same idea. We have to forge the perfect chemical ruler. And this is that master ruler. It's called a primary standard. Just think of it as the ultimate source of truth in the lab. It's a chemical that's so incredibly pure that every other measurement is going to be compared against it. It is the rock-solid foundation for everything that comes next. And when I say high purity, I am not kidding. A primary standard has to be at least 99.9% pure. And that's not just some nice-to-have detail. It is a completely non-negotiable rule. It's how we make sure every single measurement that follows is accurate and trustworthy. The precision literally starts right here. Now, here's the thing. You wouldn't use a priceless, one-of-a-kind ruler for every little job, would you? No way. It's the same in the lab. That primary standard, our master ruler, is used to create what we call working standards. These are the everyday tape measures at the lab, used for all the routine analysis, and they are all perfectly checked against that one master rule. So we have our perfect rulers. Now what? Well, now we've got to teach our super fancy multi-million-dollar instruments how to actually read them. This whole process is called calibration, and it's how we turn a machine's electronic guess into a number that means something in the real world. Okay, this is a really important point. These amazing instruments, they don't just spit out an answer like, hey, there's 5 milligrams of lead in here. Nope. They give us a signal. It could be a peak on a graph, a flash of light, an electrical current, some kind of raw data. Our job is to teach the machine what that signal actually means. And here's how we do it. It's actually a pretty straightforward 3-step dance. First, we run a blank. That's just pure water with nothing in it, to show the machine what 0 looks like. Second, we run our working standards, our tape measures, at a few different known amounts. And third, we plot all those points on a graph to create our translation guide. We call this the calibration curve. And this table here shows you exactly what I'm talking about. Look at how, as the concentration goes up from 2 to 5 to 10, the instrument signal gets stronger in a really predictable way. You see that pattern? That reliable relationship is the key to this whole thing. And here it is, the secret code that unlocks everything. You probably remember this one from math class, maybe had nightmares about it, I don't know. Y equals mx plus b. This simple little formula is the absolute heart of calibration. It's the math that lets us take any signal from our unknown sample and figure out exactly what the real-world concentration is. But there's a catch. For that secret code to work, there is one absolutely critical rule. Those data points on our graph, they have to form an almost perfectly straight line. A straight line tells us that the relationship between the concentration and the signal is reliable. If it's not straight, something's wrong, and we have to start over. So how do we know if it's perfectly straight? Well, we use a stat called R-squared. It's basically a score for how straight the line is. And as you can see from most environmental tests, that score has to be 0.995 or even better. That means 99.5% of the data has to fit that line perfectly. The standards are, no surprise, incredibly high. All right, our machine has been taught, it's been tested, and it is ready to go. It is time for the main event. Now we introduce our water sample to a lineup of highly specialized instruments, and each one is designed to hunt for a very specific type of bad guy. First up to the plate is this beast of a machine, the ICP-OES. Think of it as our super-powered metal detector. Its entire job is to find toxic elements like lead, arsenic, and mercury, even when they're hiding in incredibly tiny amounts. So how does this thing work? Well, it's pretty wild. The sample is blasted into an argon plasma torch that's burning it up to 10,000 Kelvin. Let me put that in perspective for you. That is literally hotter than the surface of the sun. At that temperature, each metal is forced to glow with its own unique signature color. The machine sees those colors and tells us exactly which metals are there and how much of each. Okay, next up, our sample moves on to the GCMS. If the ICP was our metal detector, this thing is the bloodhound. Its job is to sniff out a completely different class of troublemakers, organic pollutants like pesticides, fuels, and industrial solvents, what we call VOCs. The way it works is, honestly, like a chemical race. The sample gets injected into the super long heated tube, and all the different chemicals start racing through it at different speeds. And at the finish line, you've got this judge, the mass spectrometer, and it IDs every single chemical as it crosses, based on its unique chemical fingerprint. It's amazing. So, after all that work, the standardization, the calibration, the high-tech analysis, we are finally here. The moment of truth. We've got the data from our instruments, and now we can finally answer that original question. Is the water safe? Let's jump back to our metal analysis on the ICP. We run our unknown water sample through the machine, and bam! The instrument gives us a signal for lead, and that signal's intensity is 0.45. Okay, so 0.45. But what does that even mean? On its own, it's just a number, right? It's totally meaningless. But this is where all that prep work we did, this is where it all pays off, because we have the secret code. Remember our calibration curve? We take that signal, 0.45, we plug it right into our equation, and voila, we get our results. A concentration of 5.0 milligrams per liter of lead. We now have our answer. But is that good? Is that bad? What's the verdict? Well, we compare that number against the official regulatory limits set by agencies like the EPA, and you can see here the action level for lead is 5.0 milligrams per liter. Our sample is right at the limit. And just like that, a clear, data-driven decision can be made. You know, this whole process is just incredible. It shows you the power of science to find these tiny invisible needles in a giant haystack. It's a system of unseen guardians, really, working to keep us all safe. But it does leave you with one last big question. Our labs are amazing at finding what they're looking for. But what about the contaminants that we don't even know we should be looking for yet? That's the challenge that keeps pushing this science forward.